hear your talk.
Yeah, great. Thanks a lot for the introduction. Sorry for changing, well, this shift of schedule. I had to be home tonight, so I hope you have a bit of energy left. I will reduce a bit my talk so that you will not lose your lunch. So indeed, I'd like to talk about this, I think, interesting interaction which can take place between robotics and biology, especially for understanding locomotion. And I'll spend quite some time to study this key moment of evolution where invertebrate basically switches from swimming to walking. So the more I do robotics, the more I'm impressed by what animals do, and sometimes even depressing to do robotics. If you just look at this problem of steady-state locomotion, steady-state locomotion, handling 300 muscles more or less, beautifully, very efficient, very stable, although it's a very complex control problem, which is completely unstable, but the central nervous system solves it beautifully. It's really amazing. And animals are capable of much more, so climbing on different places, being able to handle very complex terrains. We don't yet have many robots doing this. Not falling over, even if you hope that. No, it's really stable. And really using lots of sensory modalities to stabilize locomotion, in this case vestibular and visual systems. And also what's nice in animals is this agility, ability to switch very rapidly between motor skills, superimposing motor skills. So it's in fact very rare that an animal is in steady state, as you saw here. It tends to switch very rapidly, so it's a lot of agility. And finally, what I'm really fascinated by is learning. So I don't know if you know this movie. Just amazing. So it's, I love this movie. It's maybe not very useful skills, although you could say for self-defense, but you agree with me. It had to learn these skills. It was not part of the repertoire, and I'm really amazed of how animals learn new skills. So basically, in my lab, we like to a little bit understand this. So using robots as a tool, we like basically to get a better understanding what's going on in the central nervous system to allow these beautiful skills. So it's really robots as a scientific tool. And then getting inspiration in return from biology to develop new robots and new ways of controlling robots. And more recently, we started also using some of our techniques for rehabilitation. I might have a little bit of time to present that, or I'll skip it. Okay, so let's go back to what's behind this amazing skills. So first of all, this very clever mechanics. We should never underestimate that. Lots of things are just solved by the musculoskeletal system, and that's an important fact. Then you have the spinal cord and the brainstem, which offer a lot of already control circuits, and this will be, in fact, one of the main topics of my talk is understanding this concept of pattern generators. And then, of course, you have high-level control, cerebellum, motor cortex, visual cortex, involving and controlling all this, and this learning a bit all over the place. But maybe one take-home message of today's talk, and I could almost stop here, is this, basically that you have lots of things already happening at this low level. You can have a distributed cat doing locomotion with just its pattern generators and clever mechanics. And basically there are really sophisticated circuits here which I would like to understand. And up above the brains are nice, but you almost do not need them for locomotion, at least for simple locomotion. So just one slide on clever mechanics. I will not cover this, but this, I think also here robotics has helped discover principles. So I guess you know this notion of passive walkers, where just clever mechanics without energy, just going down a slope, you have a kind of human-looking gait. And this is just kind of embedded in the mechanics. There's no controller, no actuator, no sensor. It's just the mechanics providing more or less a right cycle for you. So it's just one slide. I hope you remember this, that just the mechanics themselves are actually important. So now let's concentrate on this concept of pattern generators. That's the main topic of the talk. And if you look, for instance, at a schematic view of the central nervous system of a cat, you'll see this nice organization in the spinal cord and in the brainstem. Well, you have this, as you probably know, maybe even better than me, a very nice organization of where you have systematic inputs coming to the dorsal roots, providing sensory feedback to the circuits in the spinal cord. With the systematic outputs, the motor axons going to the muscle fibers, which are the ventral roots. And what's interesting is that you have these descending pathways going down from here to here, but they are fairly simple, or these simple signals are sufficient to modulate and activate the circuits. That will be one message. And of course, you also have ascendant feedback, basically providing proprioception feedback to the upper part of the brain. But what I find very interesting, at least from a robotics point of view, is this notion of pattern generators. So the fact that already simple inputs here are sufficient to modulate and kind of control quite complex things happening in the central pattern generators. So this notion of pattern modulation. And maybe one of the most extreme examples of this was done by Schick and Orlovsky last century, where it's not very nice, but they took a distributed cat, and if you stimulate a specific point in the brainstem called MLR, I'll come back to that later on, by just providing tonic stimulus, so just pulses, just constant pulses, they can not only initiate locomotion, have a walking gait, but if they stimulate a bit more, the frequency increases, like the speed increases, and then even more, the animal will switch to trot and to gallop. Just changing the global drive here produce completely different motor behaviors, walk, trot, and gallop, completely different ways of using the body by just changing the simple control inputs to the brainstem and the spinal cord.
I'm not sure everybody caught that this is with the cerebrate cat.
Yeah, exactly, decerebrated cat. So exactly, cut above the brainstem. So yeah, no upper part of the brain, and very brutal stimulation, absolutely. Yeah, so that, for me, is very impressive, that how simple inputs are sufficient to modulate this. So basically, just to give a little bit more detail, so this formal definition of a central pattern generator is this type of neural circuits capable of producing oscillatory patterns without such oscillatory inputs. For instance, no feedback is necessary for generating the rhythms. Groups like Sten Grillner's group in Stockholm have studied them a lot in lamprey, so, but they have been seen in many animals, both invertebrates and vertebrates. And these circuits are really distributed circuits, so you can completely isolate the spinal cord of the lamprey, put it in an excitatory bath, and if you record from the ventral roots, you will see patterns of activity which are almost identical to intact swimming, without sensory feedback, just the isolated circuit. So that's really this notion of coordinated pattern being produced by the spinal cord. And as I mentioned, it's a really distributed network, so you can find a small part of the spinal cord will still have pools of neurons which oscillate, one on each side, which will activate the muscles on the axial muscles. And one thing which is very important, sometimes people think CPGs mean no sensory feedback, and that's completely wrong. All these circuits clearly integrate a lot of sensory feedback, and the same interneurons which participate to rhythm generation are also part of like the reflex pathway. So that's why reflexes are, for instance, phase dependent, because they share the same circuit. So this notion of shaping is super important. Also from robotics, you need feedback loops, otherwise you don't control your body properly. And this I already mentioned. Simple inputs are sufficient to modulate complex outputs. And also what's interesting, kind of related, is this notion that the spinal cord doesn't offer simple only rhythm generations, but also discrete movements. So that's, you probably know this work of Emilio Bizzi at MIT, the concept of force fields, where basically stimulating specific points of the spinal cord of the frog will basically generate force fields if you like maintain the limb in some position, stimulate a point, and record a force, so basically the direction in which the limb would like to move. You can find a force field which kind of wants to bring the limb to a desired position, like kind of an attractor of the system. And what they discovered, which I find also fascinating, is if you stimulate one point, you'll have one force field wanting to bring the limb to one position. If you stimulate another one, you will have like another force field wanting you to basically go to another posture. And a linear superposition of these two stimulations will lead to kind of combination, linear combination of these two force fields, which clearly from a control point of view is great. You have two analog signals being able to generate high-dimensional movements and superimposing them linearly. And interestingly, now if you look at Stan Grailner, which is really an important figure in CPGs, he tends to define CPGs as covering both aspects, not only rhythmic movements, but also discrete movements. So both are seen as being part of the concept of pattern generators. Okay, so conceptually, I think what's interesting in this concept is first of all this notion of low dimensionality of the control signals, and then high dimensionality of what's coming out of the spinal cord. And I think this is a clever idea. It's basically, except maybe for finger movements in primates, so primates have direct control of some muscle fibers. But in many vertebrates, animals tend to have to activate pattern generators, and then these will activate the muscle fibers. So it's interesting is that the bandwidth that you need here is not too high. And also I think what's interesting is that it's a clever idea to reduce feedback delays. Time delays are very bad in a control loop, so you want somehow to shorten feedback delays, and it's a good idea to have your pattern generators as close as possible to your muscles. So this is kind of also important concept, low bandwidth of descending signals and fast feedback loops. Okay, so from a robotics point of view, the idea is basically what's interesting is to bring this concept to robotics, have this notion of pattern generators in between your planner and possibly a low-level feedback controller, but to have this kind of attractor landscape, like going to a desired posture or limit cycle behavior for periodic movement, and only then modulate this with some simple modulation. And this is a little bit the concept we like to bring to robotics. And this agrees nicely with a concept of the puppet analogy that Jerry Love at USC has proposed. He sees the spinal cord and the CPGs basically, and the descending pathways as a kind of puppet where you generate a whole movement by just playing with a few strings. So instead of playing, let's say, with 7 strings to generate all the joints directly, you just have one spring to modulate completely an arm movement, and one spring, for instance, to make them activate rhythmically. But I like this concept of having, I'll come back to it later, a few springs being sufficient to generate complex movements. Okay, so let's now go a bit, by the way, I'm open to any questions, of course. Any comments you like, feel free to interrupt. But I'd like now to present a bit more what we did with colleagues, especially with Jean-Marie Cabelguen, who is a neurophysiologist in Bordeaux, to understand this transition from swimming to walking in the salamander. Okay, so what you like to do basically is use mathematical models and try to basically understand this switch between swimming and walking in the salamander. Little by little, we like to go more to mammals as well, but so far we're mainly concentrating at this level. And here the idea is to use a robot as a tool to test some hypotheses about the organization here. And you might ask, why a robot? Why not just a mechanical simulation? And the reason is, for instance, you don't have to simulate physics here. You have real swimming, no need to simulate hydrodynamics, it's complex. So it's good to have real physics and test them in a loop with real device. It also has problems. So I guess some of you make robots, so it's much more difficult to make a robot than just a mechanical model, but it has also benefits. Okay, so let's look at this transition from swimming to walking. So why salamanders? I find them cute, of course. They're nice animals, but the main reason why we chose them is this ability of, first of all, the fact that it's a fairly simple animal as an amphibian, but this ability to have this switch between swimming and walking, this bimodal locomotion. And also what's interesting, it's a very old animal. So if you look at the body plans of the first terrestrial vertebrates, they are very similar to the modern salamander. So somehow by studying the modern salamander, we have a little bit access to the ancestor of all tetrapods, all terrestrial tetrapods. So it's a really key animal from an evolution point of view. Okay, so this is a salamander swimming. So if you look at this, this is almost exactly like the swimming of an eel or for lamprey. So it's called anguilliform swimming. Limbs are not used for propulsion. They kind of maintain against the body. And what's interesting is the animal would be able to go faster, slower, change the frequency by modulating its frequency, but it will always keep this wavelengths more or less constant. So if you plug in electrodes in the muscles here, you have a nice traveling wave from head to tail, which is maintained for different frequencies. Now, if you place a salamander on ground, it will switch to a quite different gait, where you see this nice coordination between body and limb. And let me just, I'm not sure where it stopped. And you see, interestingly, the coordination is important, and you see now a standing wave of body activation. So instead of having a traveling wave, you have a standing wave with nodes more or less at the girdles. Interestingly, frequencies are lower. This is really a slow gait, and there's no overlap between frequencies for walking and to swimming. I'll come back to that later on. So, very briefly, so what we know is, first of all, we know this type of locomotion is organized and controlled by a CPG. Like Jean-Marie Cabel-Guen has isolated the spinal cord and found oscillatory circuits. We know more or less its general organization, as shown here. We know there are also localized limbs, oscillatory centers. But a big aspect that we're missing is how the exact topology of the coupling. So here we don't have exactly information of how long the coupling strengths are. We don't know exactly what's the local network generating oscillations. That's still missing. And there we'll have to make some hypotheses to try to explain what's behind. But one thing, again, which I found very fascinating is this notion of gait transition that could be induced exactly like in the cat in a decerebrated animal. So exactly like the cat, you can cut basically the decerebrate animal to make a full lesion just above the brainstem. And if you stimulate this mesencephalic locomotor region in the animal, which is the direct pathway stimulating the locomotor system in the spinal cord through the reticular formation, what Jean-Marie discovered is that at low-level stimulation, this will induce kind of a walking gait, antiphase behavior between left and right, periodic activation of the limb, some kind of trunk movements as well, which kind of looks like more or less what would be the walking gait. And if you pass a threshold, it switches to the swimming. So just more descending excitation will make this animal switch to the swimming gait with the limbs folded against the body. So just exactly like in the cat, just changing the drive will make the switch between completely different modes of locomotion. And I find it's very fascinating. So it's kind of a bifurcation from a dynamical system point of view between two behaviors. And this is really something we wanted to study, try to understand what could be the circuit behind this. Okay, so, interestingly, birds, you can also have a bird switch between walking and flying. A decerebrated bird can make also a switch between walking and flying. Again, amazing, really showing how the spinal cord already has complex circuits for different modes of locomotion. This is basically what I explained. I'll skip this. Okay, so research questions. So first of all, we'd like to understand what type of neural circuit can produce these two types of locomotion, especially the switch between swimming and walking. Then we have a little bit this evolutionary question. So could we somehow start with the swimming network, as you see, as has been nicely studied in the lamprey? And basically, what should you do to switch to a lamprey system? So what should you add? How should you couple, for instance, limb oscillators to allow the addition of walking on top of swimming? And then we want to understand, how come just changing the drive will make you switch from one to the other? And finally, we're also wondering, why is the walking always slower than the swimming? So it's a little bit a side question.
That's a general, well, there aren't that many animals in which it has been studied, so, but you suspect that's a general...
This question of no overlap, it's a good question. We don't know exactly. We have some hypotheses why this is the case in the salamander, but it would be interesting to see how general this is. This is, I think, fairly specific to the salamander.
In the bird, was it also walking lower?
Yes, yeah. There, it seems like Low drive means slow locomotion, high drive, fast locomotion. That's kind of that's the case.
Isn't it coupled with the number of degrees of freedom you try to freeze?
Possibly.
Like if you walk as a salamander, you try to have less dependence between these segments, right? Whereas the walking movement can be, while in swimming you want more stiffness.
That's of course, yeah, you want more stiffness.
If you drive these CPGs harder, their coupling will be tighter.
Yeah.
I would think it would scale with that. Just how you want to freeze the degrees of freedom in walking and swimming.
Yeah, you would say then in walking you use more degree of freedom, so you go slow. But then flying and walking in birds, I don't know how many degrees of freedom there are.
That would be a testable prediction then, right?
Because
it might make sense for the salamander, then you test it as a bird.
That's true, yeah. No, good point. And also what's interesting, if you try to grab a salamander on grass or something like that, the panic mode is swimming. Even if it's not efficient at all, so it doesn't move forward, it looks really big panic mode. It startles probably the predator. It's not useful, but it looks like a panic mode high drive, which also relates to this. Okay, so I promised some robots. You're probably disappointed not to see robots so far, so let's show you a bit the robots first. And to be frank, we spent much more time maintaining, constructing our robots than our mathematical models. So it's really time consuming, but we managed to have this swimming robot. So first of all, we designed all the gearbox, the electronics, everything is encapsulated locally and connected with a CAN bus. And this is useful if you have leakage. It's only one element which will have leakage, not the whole set. And we started basically making a lamprey-like robot. So it's a simple robot which has all degrees of freedom aligned, so it can only swim in a plane. But you can see that already with these degrees of freedom you can start having quite animal-like gaits. And what's interesting is, I'll show you the models later on, but we program our CPG models, central pattern generator models, on board. And what will be driving the robot from a laptop will be only two signals. Basically, these two descending drives that we submit that kind of represent this MLR stimulation to the CPG model. And exactly like in the lamprey, we know that if you stimulate more, the whole thing, the amplitude and frequency increases, so you have control of speed. And if you stimulate more one side than the other, so one pathway than the other, it will turn towards the direction. So very simple, that's like the puppet thing, two strings, control speed and direction. And that's why this becomes interesting for robotics. I'll come back to that later on, but our models become in fact good controllers for the robot. Very easy to remote control with a remote control. So if you come to Lausanne, you're happy to come and I'm happy to invite you for steering your own lamprey. Okay, so I would just want to mention that many people doing very nice work in Angry Farm Swimming. I've seen Joe Ayers is coming next week. I would have loved to. He's a very funny character. He has a very nice lamprey robot he will show. Paulo Dario also has a nice lamprey robot that we developed in the Lamprey Trap project. I think where we basically my lab has some novelties more to add legs to this. So some people have tried to make lizard or salamander-like robots, but not at least they're not amphibious like ours. So that's maybe this novelties. And how we did this is basically really evolution fast forward. We took our lamprey, so took still 3 years, but not the 50 million years here, but basically we really see our salamander as a lamprey with legs. So we have a modular design so we can fit in leg modules in the chain to add walking on top of swimming. I'll show you movies later on. Okay, so maybe, let me present a bit the details behind, just for you to understand what we did in terms of modeling. And then I'll show you movies, so just stay with me a bit for understanding what we exactly did. So, as I mentioned, we had to make some hypotheses about the organization of this network. So, as I mentioned, the first hypothesis we had is that the body CPG, this system is a primitive swimming circuit. So it will propagate traveling waves, it will generate swimming. And that during evolution, we made the hypothesis that specific limb sensors have been added with a specific set of couplings going from the upper limb to the trunk and the lower limb to the tail. And so we made basically the hypothesis of this general topology. So it's something we're testing as a hypothesis. one quite important hypothesis, I'll come back to that later on, we make the hypothesis that these coupling strengths here from limb to the body oscillators, we make the hypothesis they are fairly strong. And this is needed for two things in our model. It's needed for slowing down rhythms, and it's needed for imposing a little bit the walking on top of the primitive swimming. And finally, we have two hypotheses about the building block oscillators. We make the hypothesis that somehow the limb oscillators, if you try to drive them too much, give them too much input, that they somehow saturate. And this will be the key moment where the animal will switch between swimming and walking. So below some threshold, these are active, you have walking, and if you pass above the threshold, they saturate, and that will release the swimming gait. And the final hypothesis that we had made is that these oscillators are slower. So for the same stimulus, they're just slower than the body oscillators. And interestingly, this was a hypothesis when we were making the model, but this since has been an observation. So I skipped the details, but Jean-Marie has isolated them and see that indeed, as soon as you remove them, the transaction, basically, if you release the couplings from the rest, they'll switch to slow oscillations than the rest. So this is not a hypothesis anymore. Okay, so very briefly, how would we implement this? So we took a very abstract level of modeling, basically based on just couple oscillators. So we didn't want to, since we don't know the local circuits producing oscillation, we didn't want to go into details of what happens in this pool of neurons, like 10,000 neurons in a vertebra which oscillate. We just simulated activity with a simple amplitude control phase oscillator. So a very simple oscillate with an explicit phase state variable, an amplitude state variable, and the output is like a positive cosine. So this will produce the burst of motor neuron activity from a single oscillator. And the whole difficulty is then finding a little bit what are the properties of these oscillators and mainly the topology of the couplings that could possibly explain the lamprey-like and the salamander-like gaits. And just go a little bit more in details, but basically what's nice with this simple model, is that with random initial conditions, like if you couple two oscillators together, it's fairly easy to analyze what type of behavior you get. So kind of what is like the phase relationship between two oscillators depending on parameters like the intrinsic frequency, the amplitude of the bursting, and this phase bias which is due to the couplings. So it's a fairly simple model, but we know from dynamical systems theory that it's mainly the topology of the coupling which will affect global dynamics as opposed to what is really the rhythm generation in the local network. So that's why we are allowed to make this kind of abstract modeling. Okay, so here is now a little bit the ugly part, is basically our oscillator here in principle could go to infinite frequencies or infinite amplitude if we change this or this. And that's clearly not the case in the real animal. The real animal, typically, the local pool of oscillators, the local pool of neurons will oscillate only in a given region of drive, and they will have both the burst amplitude and the frequency increasing together. That's like bigger movements, faster movement for fast locomotion, and a smaller burst and lower frequencies for slow locomotion. But that's in a given range, so you cannot go to anything. So we had to add this a little bit in an ad hoc fashion. And this is basically where we introduce hypothesis 3 and 4, the fact that for the same level of drive that will apply to the limb and the body oscillators, the limb oscillators will always be a bit slower here than the body oscillators. So if you give them, let's say, a drive of 2, just a unit less number, this will be lower frequency than here. And if we pass some threshold of drive, the limbs will saturate. Basically, the frequency drops to 0 and they stop oscillating. So it's a little bit ad hoc. It's not the most elegant thing, but at least then we have this property that we have a single input signal, which is this descending drive, which we apply to the network. And by increasing this drive, you'll see this burst increase of frequency and amplitude, and being slower in the body oscillator than in the limb oscillator versus the body oscillator for this given drive. So okay, so I went a bit fast. I skipped some details, but that's a bit the spirit of the modeling. Okay, let's go to the results. So for swimming, basically we need high drive. So we apply a big drive to our spinal cord model. limbs do not have time to oscillate, and you rapidly have a traveling wave of body activity all along the spinal cord, exactly like in the lamprey. And this is our salamander robot painfully swimming. So this is an old prototype. We always were disappointed by the swimming speed of the old prototype, but you see how this traveling wave being propagated from head to tail will propel the animal forward. And this is a little side view. I'm not sure if you see the contrast, but it's just to show that the limbs do not oscillate. It's just maintained along the body. And this has to be compared to the real animal, which swims much better. So that we still have things to improve. But basically, you see how this, if you look at the EMG activity, you see this nice traveling wave, which is a primitive mode of locomotion, like the lamprey. I'll skip this. Now, the walking is obtained by.
Okay, what you skipped. So this, let's say, reduced capability in swimming was just because of the morphological changes to your robot, or did it have something to do with how you coupled the segments?
No, it's so good question. So in fact, you will see the new prototype which swims much better. So no, but interestingly, the main thing which was make our robot swim badly is that we were missing a little passive fin. Interestingly, just adding a little passive fin, we were expecting a little bit faster speed, but it doubled the speed in the old prototype. And also the thing which is quite bad is the limbs are really badly profiled. So if you look at this side view here, these really they really act like brakes.
Mm-hmm.
So just the profiling, the drag coefficients are really poor, and that's the second thing. And the last thing is torque limits. The new prototype has bigger motors. So, but the principle you'll see later on. In fact,
it's interesting, right? Because actually the whole control itself is generalized.
Yeah, that's true. Yeah. So walking, as I mentioned, is low drive mode. We just are below threshold for the switch between swimming and walking, so below threshold. The big difference now is limb activation in antiphase between forelimbs and hind limbs. And what's interesting is now this is much slower, so the body oscillates are much slower, and all the trunk elements are here in phase. So these are the four trunk elements. The four tails elements are in phase as well. And you see this abrupt change of phase which corresponds to the S-shaped standing wave. And this is how it looks on the robot. So I guess you can see here quite well the standing wave. If the robot comes back, you see here the nodes, and you see the nice coordination between the standing wave and the body movements. So since the robot is waterproof, we can take it out when it rains. It's a nice thing. And you might just realize we have cheated compared to nature. So we have a single motor per limb, which made our design much simpler and still was sufficient to explore how basically the stance phase, when the limbs are on the ground, coordinate with the body ondulation. So it was a simplification, but still a very useful one from a robotics point of view and not too relevant from a neuroscientific point of view. And basically here we're quite close to relative in terms of speed relative to the body size and the cycle duration of a real animal, so it's similar speeds. And we kind of have this result that if you look at muscle activity on one side, you have this nice coordination which explains the standing wave of the animal. And here the kinematics again are quite similar. Even if our kinematic plan is much simpler than this, we are in fairly good agreement with what the salamander does. Okay, so yeah.
So how difficult is it to tune these oscillators? So you have a method to say this is how I want to tune it mathematically, or you just have someone trying?
Yeah, in this case we have some methods like where we can run optimization algorithms. We do quite some bits in optimization, but here in this case it's just systematic search. So the number of parameters are fairly low because we have some symmetries. All oscillators have the same amplitude, same frequency. So we did some very systematic studies to see, for instance, what is the best optimization of the amplitude. And interestingly, you come back to what your animal does. So if you try to have too big amplitude, so if your body is too much bent, you lower your speed. If your body is not bent enough, if you keep the body straight, it also lowers the speed. So the optimum is close to what the animal does. So in this case, to answer your question, we had enough low parameters that we could systematically test them and find the right combination.
Auken, I also have a question to the spirit of Tony earlier. So if you say this is a good agreement in the kinematics, right? But if I want to be Tony about it, then I'll check with the details. Then actually also many differences.
Yeah, absolutely.
So when is it, how do you really define a good match in this case?
Yeah, no, so this is a bit qualitative, so it's a good point, and we have even a newer prototype, which I'll keep secret, where we go in exactly that. In fact, we now have amazing, well, maybe I'll just show you one little bit of that. We have amazing...
The computer science trick. He also, when he challenges these guys with the models, oh, but didn't you read this paper of some hidden species somewhere in China? It hasn't been published yet, but it's all
Okay. No, here I know it's from my lab, so I know it. But, indeed, there we'd like to go into much more complex dynamics, especially a salamander can just move one limb, it can walk backwards, it can do all kinds of things, which we cannot at all in this simplified model. So we now have very nice X-ray data. I didn't know it exists, but Martin Fischer in Jena has a wonderful X-ray machine, 500 frames per second, where you see all the bones. Cool. And the animal survives somehow. And I'm not sure if it's allowed in humans, but basically we have very fine kinematics, and that was directly used for the robot design, which I'll keep a bit secret. Yeah, right. Yeah. But then we can go in much more quantitative things. So here it's still a bit qualitative. Yeah. Okay, so I think every good talk needs a Terminator slide. So this is my Terminator slide. It's a kind of a joke. We do bit. So this is the Terminator slide. So I'm not sure if you can see the contrast. So it's very well. I hope you have seen the movie. This is the what remains of the first Terminator robot, and he's chasing this poor lady and being able to move forward, looking quite horrible. I just wanted to show we can do the same. And maybe I'm biased.
It's very scary.
Yeah, exactly. I'm biased, but I find ours a little bit cuter. But so it's a little joke. So just
make one that's chasing you, and you're crawling.
Yeah. Well, though it's you cannot see the size, but this is still you would be much bigger next to it. So even that would not.
Impressive.
Yeah. Okay. So more seriously. So we can now explore is like gate transitions going from slow drive to big drives dynamically. So this is really on the robot. You can really play dynamically with this. But in this case, if you just increase it slowly like this, you see exactly what has been seen in the MLR stimulation. But basically, at some point in a whole range, you have the walking gait going slightly faster or slower with the standing wave mode. And at some point, you have this saturation of the limbs. They become basically tonic. They don't oscillate anymore. And that's when you release very rapidly the traveling wave mode. So that's when you, first of all, go to traveling wave here. And also you go to higher frequencies. You can see here that at some point things accelerate at this stage. And this is like the instantaneous frequency. You really jump from a slow range here to a fast range here, which is in fact exactly what, if you look at the animal, for some reason, if you just record its frequency during stepping or swimming, so the cycle duration just the inverse, but if you look at the range of frequencies here, there's a gap. So always either slow walking or fast swimming, but you never see a slow swimming or fast walking overlapping. And at least to come to your question you had before, we are hypothesized this is really due to the slowing down effect of limb oscillators. And interestingly, this is also kind of agreement of the work being done in a group in Bordeaux working on metamorphosing frogs. They see also the frogs, when they get the limbs, the limbs are always oscillating much slower than the rest of the axial circuits. So this is due basically to the slowing down effect of the limb oscillator. Okay, well, you saw this moving gate transition. This is the animal going up a ramp, and looks like as soon as there's some tactile information, there's the switch. So we're even thinking maybe the switch could be at a very low level, so we don't know yet. But as soon as there's a tactile information, we believe the animal lowers down the drive to the spinal cord. And you see this very smooth transition. Just in one cycle, it goes to the walking gait.
Oh, there's a slope.
Yeah, it goes up a slope, exactly like here. It does exactly here. We cannot replicate it here, the low-tech version, but basically we go up a ramp here. And here, the brain, it's Alessandro, the postdoc. So he decides when to lower down the drive. So we don't have yet sensory feedback in this prototype. But when he lowers down the drive, I think the movie will replay, you see that it very rapidly does this transition here, that it will go into the slower walking gait as opposed to the swimming gait. So I think now is more or less the moment. It takes maybe one half a cycle to stabilize, and then you get into the walking.
Skips a beat.
Yeah, yeah.
Actually, what I realized, you have to slow down when you walk also because this is the friction, right? Because initially you're in a viscous medium, so
Yeah.
other frequencies can be sustained while in walking.
Absolutely,
Because
yeah.
if you maintain a high frequency, the friction will just not help you anymore to propel yourself.
Very good point, yeah. So in fact, we were often quite frustrated with our robots slipping too much if we're going to high frequencies. And then we saw many movies of salamanders doing exactly the same. It was for me a great thing.
Being frustrated.
No, yeah, at being slippery or slipping, yeah. The state of frustration, I don't know, but at least the slippering, yeah. Okay, so I often get the question, is it really useful for the animal or the robot to undulate the spine as much as it does on the ground? And of course it does. Basically, just simple kinematic reasoning can show you that you can increase the stride length. That's this limitation of lizards and salamanders. They have the sprawling postures as opposed to mammals. They can move below the body. So that's why the animal does this standing wave undulation. But here, just to illustrate this, and mainly for fun, we have a race between 3 robots, where this one will use the salamander gait, the normal gait. This one will not use its spines. We'll just keep it tonic, straight. And this one will use a body undulation, but just the wrong phase relationship between body and limb. And we can take bets here of who wins, but you can clearly see that this one gets 40% faster than this one. So it's really worth doing this body undulation. And this movie is important for me because it shows it's good to undulate, but do it properly, otherwise you look silly. And also you really have lower speed. So this is part a bit of your question of how to optimize like body amplitude. This is how we also fine-tune a bit the amplitude to get optimal speeds. Okay, so I think what's interesting possibly of this model is this notion of explaining the gait transition from walking to swimming. And what's also possibly interesting is from an evolution point of view, what it tells is that you don't need to completely change the swimming circuit. You can reuse it for walking, especially for having this S-shaped standing wave. But what you need is just add properly this limb center. So it's probably what evolution did, is just add the layers on top of this primitive circuit. And there's still many things to explore. So what we're currently doing, and I could present 1 hour almost talk of this, is several things. But let me just very briefly present these things here. And I think then I will stop. So I will stop the talk here. But first of all, we're now quite happy to have faster swimming. So this is the new prototype. And in fact, if you remember, the first lamprey robot I showed is in fact the new prototype. So we simply have more powerful torques, motors. We have the limbs, which are much more profiled. So we find some tricks that they're more profiled when they fix against the body. And now, if you look at how much the body advances per cycle duration and relative to body duration, we're quite happy in the sense that we go with this slope in one cycle, the animal goes with this, and we are very happy to see that our slope is slightly bigger. And before, the slope was really lower. So, and to answer your question, this is now really due to the fin here, the limb profile, and higher torques. In fact, we could do a study to see how each of these components helps. That would be useful. Yeah. The walking, so we're exploring with fingers, so to reduce a bit slipping. Here, we can do what the salamander doesn't do, is very fast gait. So we have some slipping here, but we can go faster than the animal. Well, you should just realize this animal is still 1 meter big, so it's a big salamander. So it's not as small as this one, of course. Maybe one thing which is very important for me is now to extend this work to go to richer motor skills. So this is in the framework of the Lampetra project. We wanted to systematically see what can the animal do in addition to just swimming and walking. So And it can do much more. So of course, it can do, well, this is what you saw, swimming and walking. But it can do things like, I'm not sure in which order they come, but they can do, oh yeah, first of all, they can do walking in the water. So it looks like if there's some tactile information, they will have like a walking gait in the water, which interestingly is a bit a mix of walking and swimming. So you see a bit of traveling wave here. So we want to study this. And here it can do things that our model cannot do at all. So this is like, you can see decoupling between limbs. So you see this pace-like gait. So this is really shows more finer, like less strongly embedded patterns than we have had so far. This is walking backwards. This we still haven't studied. And there's a whole set of behaviors that we haven't studied. But this is, I think, very important for the CPG community, because sometimes people think CPGs just produce fixed patterns, and that's completely wrong. But we need to show, indeed, how can you get this more complex behavior? And the big question is it sufficient to add more descending pathways? Just activate some part of the network, basically add more strings to your puppet? Or do you need more specific circuits here? And for instance, for walking backwards, it might be that you have some circuits yet that we should add also at a lower level. So clearly this is where modeling can be useful to explore a bit what's the most likely explanations. Okay, and this kind of goes to the puppet analogy. So I now have probably half an hour of talk for the rest, but maybe I'll just tell you what we're interested in doing in robotics. So we would like to bring this now to robotics. So this is, I think this CPG concept is now taking quite some interest in robotics, because the idea is instead of doing kind of traditional planning is to do more like attractor dynamics. Have your gates implemented as dynamical systems. Aim at entrainment between the mechanics and the controller. So like a limb is also an oscillator, so you want to couple your neural oscillator to mechanical oscillators. And this notion of simple online trajectory modulation with simple signals is interesting. And this notion of lower dimensional descending signals is clearly useful for learning and also for control. So we like to basically see how, using a little subset of these pattern generators, we can use them as movement primitives for more complex movements. So I have a whole talk, so I'll just go to the end directly, and I'm sorry that I'll skip this. It's all on the web. So I was a bit optimistic, so just go to the end. So for fast readers, you might be able to get some. Yeah, maybe if you allow me, just for fun, this project. Nice. Yeah, because this is a crazy project, and sometimes I think universities need to do some science fiction. I'm a science fiction fan. So this one came about since we design modular robots, but they are not self-reconfigurable. It's a whole field in robotics by itself. There are many active teams. And at some point, there was a call for funding at EPFL to create intelligent furniture. And being a bit opportunistic, we decided why not have self-reconfigurable robots as furniture? Basically having little building blocks, and that this conference rooms, like for instance in the morning, would not exist. All the furniture would create itself in the morning with somebody logging in, asking for a set of stools. Later on, somebody else wants tables and then chairs, and everything reconfigures. So the idea is to explore what could we do in this field, and what could we do. And everything is summarized in this little movie. So basically, idea of little building blocks which by themselves cannot do much, but by gripping to each other and gripping to the ground, basically the idea is that they can coordinate to do self-construction of objects. It looks a bit strange, silly, but
the table.
Yeah, exactly. It's a quadruped robot, so we don't want to do locomotion, of course. So we have some hardware, so the simulation goes much faster than the real hardware, but this is the concept. So this is for us one module, and you should see like 4 half spheres, each can rotate compared to the other. And they have this dynamic connector. So each of these faces can have grippers, which allows to connect to another face and create a rigid connection. And once you have that, you can do, first of all, some kind of locomotion over the grid. So you can, a single module can move around in a grid. I'll play this movie. And thanks to this, you can also couple things together, create more complex structure. A little example here. So we still have to do quite some things in hardware. But the whole dream is that having these little building blocks, we provide them to people and see what they come up with. So designers might create some, I don't know, artistic sculpture that moves over time, or you could maybe fix a spotlight to this to follow somebody, or a loudspeaker fixed to this. So you could possibly use it for other things than furniture.
Screw in light bulbs.
Yeah, yes, yeah, if you. And of course, we are mainly interested in furniture. I think there are lots of things to do there. And we're exploring also what could be additions. Clearly, you don't want to create a whole tabletop with modules. You probably want to be able to manipulate a few objects. Like in Lego, you have more than one piece that you fix together.
But the control does not have CPU.
Yes, it has CPGs, of course. So I would like to have a sticker with CPG inside at some point. So that's why the beauty of CPGs, it's perfect for this distributed control. So what you see here is, I'm not sure why this one doesn't play. Oh yeah. So what the whole idea is to have CPGs, a set of oscillators in every element, where the topology of the coupling will match the mechanical topology, and have learning on top of that. So if the table gets a new limb or you lose a limb, you do some online learning, possibly helped by a database of good solutions, so that you explore good gates.
But the reconfiguration process itself will not have CPU.
No, the reconfiguration, interestingly, is a very traditional planning problem. It's more like chess, A-star, heuristic problem. A very complex one, by the way. This is your table running away. It should not carry the beers, though, but that's... Okay, so this might be your future in 20 years, and I spent 20 years here to make sure you forget I promised this. Okay, so take-home message, don't underestimate your spinal cord. Basically, there are really sophisticated circuits there. You have everything to do modulation of speed, direction, and type of gate, and much more. And this kind of technology is useful for robotics, as I tried to explain briefly. So mainly this notion of reducing the dimensionality of the control problem. So this is the whole team that did the real work. So I do a bit the hand waving. And just for fun, this is, well, if you want the papers, the movies, they're on this website. And this is, for fun, a little race between our Lamprey robot and Kostas Karakasiliotis, the fastest PhD swimmer we ever had. And look at how our robot still won the race. Okay, thank you very much for your attention.
Great, Alka, thank you very much. Questions? Sure.
Your approach is tied rather tightly into the traditional swimming and gait and locomotion thing, where oscillators are the obvious thing in the central pattern generators. But the spinal cord has another contingent of sophisticated mechanisms, which are all the old traditional spinal reflexes, like cross-extensor and withdrawal reflex and patellar reflex. All of these, if they are not like they are portrayed in the textbooks. They have little maps, little sensory motor transforms, like Schomburg shows in Lund. And if you add those, you might be getting out of simple control. If you add those to your, you might be getting some of those other skills, like the walking backwards.
Absolutely, yeah.
So
Yeah. Also, this is a very good point. So especially in mammals, like if you look at the cat, all the reflex pathways you identified by people like Serge Rossignol and others, you really see hugely complex sensory feedbacks, which are kind of probably modulated by the CPGs and the interact, so like reflexes are phase dependent. And then you can have much richer behavior than the simple behavior. So
I bet that they use some of the same neurons.
Yeah, the same interneurons will receive a part of the rhythm generation and the reflex. Yeah.
Good question.
Yeah, the salamander robots, the segments were completely independent and you had like a distributed controller there.
It's so far we mainly control everything from the head. So everything is programmed in the head, but we now have everything ready to do really distributed control, and we could make a creepy video where we'd have like two parts move. Yeah.
Okay, so the control from the control of the frequency which comes offline from another person, it would initiate the head that propagate to the tail, or how
No,
does it happen?
yeah, no, it's really a phase lock regime. So all oscillators receive the same drive, and from random initial conditions, they will rapidly stabilize into the phase lock regime, which is due to the coupling. So it's really a dynamical regime that's due to the coupling, and everything receives, every oscillator except for left-right, where left receive more than right. Otherwise, they all receive the same input.
Does the actual morphology of the robot does play some role in determining the phase? Does that happen?
Yes, yeah, I think so. Well, so far it's kind of built in the network, but we now have a whole hypothesis that sensory feedback plays quite a big role to shape this S-shaped standing wave. Especially if you look at the aquatic walking, it's a little bit in between swimming and walking. So our hypothesis is that it's more a peripheral feedback mechanism which explains this. And interestingly, what's interesting is the standing wave is quite in agreement with the forelimbs and hind limbs being in antiphase. So you could use, for instance, the coordination from the body CPG to coordinate limbs, for instance. So that is now work in progress to study that. Yeah.
Aaron,
Point. Yeah.
just a very small point. Your presentation reminded me of some presentations, one or two I've heard some time ago on C. elegans, a much more primitive organism, and I just wondered if there's any evolutionary connection, or whether it's just totally separate, evolved solutions to similar problems.
Yeah, no, so it's a very good point, because the anguilliform swimming had been used for spermatozoid bacteria. It's one of the mode of locomotion which scales quite well with different Reynolds numbers. So
you know Netta Cohen's work and
yeah, exactly. Yeah.
Birmingham in mind.
Yeah.
I don't know what well.
So and C. elegans have also CPGs, and they have, the good thing is they have only this 267 neurons, or like this, they're even numbered. So they are very much more tractable to explore than this. But it's the same principle: coordinated patterns of activity propagating and producing anguilliform swimming. Yeah.
These things get rediscovered.
Yeah.
So it's fairly intuitive how these simple pattern generators are used in cyclic motion, but in motion that has a less obvious cyclical structure like reaching, is from a robotics perspective, that problem still hasn't been solved gracefully, and I wonder if there's some insight that can come from the simple pattern generator approach.
Yeah, I think the CPG approach would be a bit in agreement with the equilibrium point theory more approach, where and the force field, the notion that you activate a force field. Just at the beginning, I mentioned briefly Emilio Bitti's force field, that you have also discrete pattern generators activating a single point attractor. And one thing we did on the iCurve was exactly that: is superimpose discrete and rhythmic activation, so that you can have visually guided feet placement. So you do kind of reaching to the ground during cyclic motion, and this would be discrete corrections. And so this is indeed, this will be part of this repertoire of both discrete and cyclic dynamical systems that you can activate at the right time for producing coordinate movement. That's still a big topic of research, but you absolutely need it, you're right. Locomotion is not only cyclic.
Other questions? No? Okay, thank you very much.